Okay, Wilson, we have about 30 people tuned in live, and we'll have a few more people and more folks trickle in as the time goes on. But everybody, welcome to the first live Spearbit seminar that's public and available on Twitter. Thank you, everybody, for joining. Today, we're going to be discussing from Wilson his presentation on the Nova proof system. Wilson was one of the authors on the paper that discusses what's now been renowned as the ZK Bug of the Year on Nova. Wilson is a PhD candidate advised by Dan Boneh and a member of the Stanford Applied Cryptography Group. His research primarily focuses on zero-knowledge proof systems and related primitives. And without further ado, Wilson, I'll go ahead and hand it off to you.
Thank you. Hi guys, so today I will talk about our paper, Revisiting the Nova Proof System on a Cycle of Curves. This is joint work with Dan Boneh and Srinath Sethi from Stanford and Microsoft Research. So incrementally verifiable computation, or IVC, introduced by Valiant in 2008, is a method to efficiently prove the outcome of some continuous iterative computation. So here in this diagram, you can imagine you have some initial value z0, you have some function f, and the claim that you would like to prove is that some value zi is the result of repeatedly applying the function f I times. So when would this actually be used? So some modern day examples are, for a slow f, you would like to prove the outcome of some verifiable delay function. So imagine f takes a certain amount of milliseconds or seconds to execute. You want to prove that you've done a certain amount of delay. So you prove that you've done I iterations of this slow function f. All the other things are like ZK EVMs. So you can view ZK EVMs as state machines. So instead of z being just an arbitrary element, it's now the state, and f is a state transition function. So you want to prove that after certain amounts of state transitions that you receive the current state. So our work, in the grand context of things, describes a soundness vulnerability in the original Nova IVC implementation. We implement the attack generically for any choice of function f, whether it's a VDF or whether it's a ZK EVM, etc. And to demonstrate the vulnerability, we generate a fake proof of 2 to the 75 iterations of the min root VDF in only 116 milliseconds. So in the paper, I listed 1.46 seconds, but we're actually way faster. It's because I forgot to compile in release mode. And so the numbers from the paper are from debug mode. And so if the Nova IVC scheme had actually been secure, this would have taken thousands of years. So the fact that we generated an accepting but fake proof means that the IVC scheme was actually insecure. Furthermore, we patch that bug and we provide a secure compiler from these folding schemes to IVC over a cycle of curves. So what should you take away from this talk? Roughly an intuition on what folding schemes are. We're not going to go over their construction, but we'll go over a little bit of their structure. How IVC is actually constructed from these folding schemes. And once we understand how IVC is constructed from these folding schemes, we can actually go into the soundness vulnerability in the original implementation of Nova. So first off, folding schemes. But in order to describe folding schemes, I'll have to do a brief review on constraint systems. So an R1CS constraint system consists of 3 matrices. They're accompanied by an instance witness pair, X and W. So you can imagine X as the public outputs and W as the private inputs. And so an instance witness pair XW satisfies this constraint system, which consists of 3 matrices, if they satisfy the equation on the right, in the sense that the matrix vector product of AZ, Hadamard product BZ equals CZ. So you can think of Hadamard product, which is that little circle here, as component-wise products. And so Nova, which is the KST paper, introduces a notion of relaxed instance witness pairs and also relaxed RNCS. In particular, these pairs satisfy the constraint system if they satisfy a more relaxed notion of RNCS. In particular, instead of strictly satisfying this equation, we also are allowed to scale by a scaling factor, and also we have this additive error here. And so it's like we satisfy the original constraint system, but with a little bit of error. And so now these instance witness pairs change a little bit. Instead of just the public outputs, we also add two more commitments, a commitment to the witness and also a commitment to the error vector here. Furthermore, the witness also contains the error vector. So the difference, in summary, between relaxed instances and witnesses to regular instances and witnesses is now that they satisfy the constraint system, but with a little bit of error and a little bit of scaling. So because this relaxed notion is a generalization of just regular RNCS, we should actually be able to test whether these instances satisfy RNCS without any error. And so the way to test if this instance is capable of satisfying RNCS without any error is, since we have a commitment to this error vector, we just check that the commitment is actually a commitment to the zero vector. And we also check that the scalar is just 1. And so we're able to see if the instance satisfies RNCS, the constraint system, without any error. Furthermore, because there's this error, it's actually trivial to come up with instance witness pairs that satisfy the constraint system. The intuition here is you literally just set the error vector to whatever is needed in order to make this trivial pair. So I'll denote these as U-bot and W-bot, but all it is just some random instance witness pair that satisfies this constraint system. So what are folding schemes then? The goal of a folding scheme is to reduce the claim that two pairs satisfy the constraint system to the claim that a single pair satisfies the constraint system. In the sense that if this single pair satisfies the constraint system, then with high probability, both of the original pairs satisfy the constraint system. So folding schemes, more concretely, consist of two algorithms: a folding verifier, which takes in as input two instances and reduces this down to a single instance. A folding prover takes in both pairs and reduces it down to a single pair. And so the security of this is that if this pair is satisfying, then we should be able to extract witnesses for these prior instances here. So in the sense that these instances would actually have witnesses that would satisfy the constraint system. So why do we even care about cycles of curves, and what are cycles of curves? Well, in order to construct IVC, we'll actually have to describe the folding verifier in the constraint system itself. So we're going to actually have to express the algorithm as constraints. Now, what does the folding verifier actually do? The folding verifier will end up taking a random linear combination of some field elements. And so expressing this as field constraints is pretty simple. But it'll also have to take a random linear combination of group elements, in particular, the commitments themselves. So how do we actually express these group operations within a constraint system? Well, I guess we're going to have to dive deeper into what these groups actually are. So if we look into the group operations, this group is actually an elliptic curve group over a field. This is called the base field. That's different from the scalar field. So the scalar field has order p, which means that the size of this field is a prime p that is equivalent to the size of this group. this base field has size q, and it's different from the scalar field. Now, an elliptic curve group, each element consists of a pair of field elements over fq, such that they satisfy some elliptic curve equation. Now, in order to express these group operations as constraints over the original scalar field, we'll have to express these FQ operations, or the base field operations, as FP constraints. And so it basically boils down to, in order to express group operations in a constraint system, we'll have to express the base field operations over the scalar field, which involves a lot of non-native arithmetic. You'll actually have to express modular multiplication and modular addition, but over the original scalar field. And so this will actually end up being very expensive. And so a cycle of curves will actually allow us to express the folding verifier in a more efficient manner. So the idea is, why not just express these group operations as FQ constraints instead? So we see that each group element is represented as a pair of these field elements. So why not just represent them using that field anyways? So that's where a cycle of curves comes in. So what is a cycle of curves? It consists of two groups. One group has order P, and it consists of elements from this FQ field. Now, its scalar field is a field of order P, but now its base field is a field of order Q. We also have a secondary group, GQ, whose scalar field is FQ, but whose base field is FP. So this is a little bit of a confusing diagram, but the summary is that a cycle of curves consists of two elliptic curve groups, GP and GQ, such that the scalar field of the group will be the base field of the other group, and the scalar field of this group will be the base field of the other group. Now, if that didn't make sense, I have a cleaner summary that is something that you'll just need to carry on. All you need to know is that in order, I guess this is the summary. If you have some constraint system over one field, and we want to fold pairs for that constraint system, we simply can efficiently represent them as constraints over a different field. So I have two constraint systems now over two different fields. To fold these pairs, we can simply just represent this folding algorithm as constraints over the original constraint system. And so now we have two different constraint systems over two different fields. And to fold their respective pairs, we just have to express that folding algorithm over the other constraint system. So recap so far, we described IVC as a method to prove the outcome of some long continuous iterative computation. We discussed folding algorithms as a pair of algorithms, a folding verifier and a folding prover. And the idea is that we can reduce the satisfaction of two pairs to the claim of a satisfaction of a single pair. And we discussed how to efficiently describe folding algorithms in two different constraint systems over two different fields. So now we actually have enough to discuss our compiler from folding schemes to efficient IVC over a cycle of curves. So what changes with a cycle from the normal description of IVC? Well, instead of proving repeated applications of a single function using a single constraint system over a single field, now, as you can imagine, we have a pair of functions operating over two different fields and a pair of constraint systems over two different fields. Hint, these are the constraint systems that we saw in the prior slides. Now, what is the claim that we'll have to verify for IVC over a cycle of curves? The claim is this. that we want to prove I iterations of a pair of functions over a pair of elements. And so now, instead of the diagram having just one chain of evaluations, we have two chains of evaluation. So the verification algorithm for IVC will verify the claim that we've done I iterations of a pair of functions. It'll take in a proof of this claim, and it'll output accept or reject. So how is IVC actually constructed? So at each step, our IVC prover would like to prove the execution of a pair of functions. So here I've labeled in these big boxes different steps of the IVC prover. Now at step I+1, we take in the pair of function inputs, and after this, we should output a pair of function outputs. And so in this step, the IVC prover will have to prove an execution or two executions. So what we can do is we can actually have a constraint system which applies one step of their respective functions. So this constraint system here applies one step of the first function, and this constraint system applies one step of the secondary constraint system. And so the IVC prover will prove that these constraint systems are satisfied for every step of the computation. So diving in a little bit deeper, the prover not only has to prove the satisfaction of each of these constraint systems, but will have to prove the satisfaction of all prior steps. And so how can we actually do that? Well, with a folding algorithm, we can just fold all these claims together. So what will end up happening is that in step I+1, we have a constraint system. We have a pair of constraint systems, one which proves an execution of the first function and one which proves an execution of the second function. We can actually represent that claim as a strict instance, UI1 and UI2. Now, after I steps, we'll have I of these instances. Now, I have here these new instances, which I'll call the accumulators. And so the intuition of what these accumulators are is they accumulate all of the I prior claims. And so if this instance is satisfied, it's as if we actually did apply I steps of the function. So this accumulator here will be all these items folded together. And similarly with the secondary constraint system as well. So at each step, we produce instances and we fold them into an ongoing accumulator, such that if these accumulators are satisfied, that means we actually performed all the I prior steps. So zooming into the construction a little bit further, each step takes in the function inputs, takes in the accumulators from the prior steps, but also takes in a strict instance for the secondary constraint system. And so now, as you can imagine, this constraint system applies one step of their function, but also folds the strict instance plus the accumulator for the secondary constraint system. And so we fold these together and we get this new accumulator for I+1 iterations. Now, the satisfaction of this constraint system, we can represent as another strict instance. And this gets folded with the accumulator that we got in as input for the step. And so now we have an accumulator for I+1 steps. And this constraint system also applies one step of the secondary function. And so now we can sort of repeat this argument. We can express the satisfaction of this constraint system as yet another strict instance for the secondary constraint system. And so what do we have in total? We have two new function outputs. We have a strict instance for the secondary constraint system. And we have now two accumulators, which accumulate the successful execution of all the prior I steps, including this most recent step. And so you see here, we have function inputs, function outputs, old accumulators, new accumulators, new input strict instance, output strict instance. And so the inputs and outputs of every IVC step are identical. Cool. So now I can actually zoom in on the constraint systems themselves. So I lied a little bit. The instance doesn't actually just output a function output into accumulators. Instead, we actually output a hash. And so you can think of this x0 hash as constraining the inputs of the next constraint system. And x1 will constrain the outputs of this constraint system. And so in addition to taking in the function inputs, the strict instance, and also the accumulator, we also take in an index, which helps us keep track of which IVC step we're on, but also the initial value for the IVC claim. And so this is like the base case value. And we'll just like basically increment this index, but also copy this forward. So the first set of constraints, as I was saying, are the input constraints. And so we check if this instance's x0 hash contains all the elements in the witness. So notice how every other element in the witness for this constraint system is contained within this x0 hash. Furthermore, we just check if this is actually a strict instance. We apply one step of the function in the constraint system, but we also fold both pairs. Now we do the output checks. And so we check that the x1 hash, which constrains the output, is actually equal to the hash of one increment of the index, the original base case value, the function output, and also the new folded accumulator. But all is fine and dandy, except for what is this little copy constraint actually used for? So let's follow things. We check that this x0 hash is equal to the x1 hash of this instance here. So notice how there's like a 2 to a 1. And so the way to think about these hashes is that one thing is that they're uniquely representable in both fields. So this copying sort of makes sense. We're just copying a hash from both fields. But the purpose is, since we have two constraint systems, we would like to line up the output of this constraint system with the input of the same constraint system. And so what will end up happening is that this sort of copy constraint will shift the hash checks to be in the appropriate constraint system. And so I'll have a diagram in the next slide, but I'll just take a moment so that people can absorb this. So the constraint system does some input checks. It applies one step of the function. It folds the pairs. It checks the outputs, but then also does this copy constraint here. So what does this copy constraint do? So I've labeled in orange anything related to the constraint system for the secondary constraint system, and I've labeled in purple all the things related to the primary constraint system. And so in the primary constraint system, we do hash checks on the inputs and we do hash checks on the outputs. But now I would like to connect the purple output to the purple input. And so all that copy constraint does is it simply just forwards the purple hash to this original constraint system. So this sort of copy constraint shifts the hash checks to be within the appropriate constraint system. And similarly with the orange, in this purple constraint system or the primary constraint system, we don't actually care about these secondary constraint system hash checks. So then we just do the copy constraint and we shift it to the secondary constraint system. And so it's sort of like a diagram tracing. You want to connect these outputs to the inputs, and you want to connect the prior output to the input for the next constraint system. So it just makes sure that like the hash checks are aligned with the proper constraint system. So what does the IVC verifier actually do? So the proof pi will consist of both those accumulators that we produced in every IVC step, plus the final strict instance. And so the IVC verifier takes in the claim that we've done I iterations for both functions. It takes in the IVC proof pi, which is above. It checks if that final instance is strict. It checks if all those pairs are satisfying for their respective constraint systems. And then this is where it gets a little bit special. We now have two hash checks. So it checks if the x1 hash is the expected hash of the elements in the claim, but also checks if the x0 hash contains the expected elements in the claim. So here, these accumulators should be the accumulators we had in the proof, and the claimed index, the claimed base evaluation, and the claimed evaluations should all be in this original claim. And so it turns out that if your verifier does this and does all these checks, that this is actually secure. So we prove in our paper that this verifier actually is secure. So what went wrong with the original Nova verifier? Well, the proof contained an extra strict instance for the primary constraint system. Okay, so containing an extra one doesn't necessarily makes you insecure. So what was different about the verification algorithm? The verification algorithm checked that this additional pair was strict. It checked that this additional pair was satisfying. But now this is the subtle change that caused everything to be vulnerable. Instead of checking the x0 hash for the secondary instance, it checked that the x1 hash of the primary instance was equal to that same hash. Now, why would this intuitively make sense for when I guess the original Nova IVC scheme was coded up? Well, remember how I said the x1 hashes constrain the outputs. And so you would think that, well, this is a secondary constraint system, so we should constrain the secondary function's outputs. And similarly, this is the primary constraint system, so we should constrain the primary constraint system's output, right? Here's zi1, which is the output of I evaluations of the first function, and here is z2, which is I evaluations of the secondary function. So I can see where this sort of check was intuitively, I guess, done. But we know from our diagram that this instance is fed into this constraint system. So what ends up happening is that copy constraint copies x1 into x0. So we should just be able to check if this hash occurs in this x0 hash here. But it turns out that by doing so, if you only check the x1 constraints, there's actually no constraints on the x0 hashes anymore. And so we can set the x0 hashes on the right side to just trash, and the verifier never checks that. And so that's the key difference that caused the vulnerability. It's that the verifier didn't check these x0 hashes, and so we can set them to arbitrary elements. And so how does the attack go? We can split the proof pi into two halves, where we have the strict instances, but we also have the accumulators. Now, that vulnerable verifier could actually be split into two independent checks on both of these halves. And so the first half consists of this strict instance and this accumulator. We checked if it's strict, we check if both pairs are satisfying, and we check the x1 hash as expected. And so this accumulator should be the one that's contained in the hash, should be the one that's in this half of the proof. And there's a symmetric set of checks for the other pair. And so notice how these checks are symmetric. All I've done is just replace all the ones with twos and all the twos with ones. And notice how neither of the checks check anything about the x0 hashes. So how does the attack proceed? We can choose any arbitrary starting values. It doesn't matter. And we can also choose any arbitrary preimages. So you can just imagine these are just random values. What we'll end up proving is the claim that we've done I iterations of whatever function we're claiming, but with these being the preimages right before the last step. We first generate the malicious pair so this is just the front half of the proof. And symmetrically, using the same technique, we'll actually be able to generate the other half of the proof. It's because those checks are symmetric. And so you can just repeat the algorithm we use to generate this malicious pair to generate this malicious pair. And then we simply output the malicious proof, which just consists of both the pairs. And so to reiterate, what are we trying to prove? We're trying to generate a fake proof that we've applied I iterations of some pair of functions on these values here. And what's interesting is that we're actually able to have an influence on whatever the output claim is. And so we just choose any arbitrary single preimages of those functions. So the main crux is how do you actually generate these malicious pairs here? So the key idea is that since the x0 hashes are never checked, what we can do is we can just run a single step of the IVC prover. So what is the runtime of the attack? Just running a single step of the IVC prover. But this time, we're going to run the step on maliciously constructed inputs. And so remember how in every IVC step, we took in some function inputs, but also some accumulators. And so in this case, in this step, we'll take in accumulators which are not satisfiable and instances which are not satisfiable. So we have to cook up this instance here such that all the hash checks pass, but we end up producing two accumulators, one instance and one accumulator that satisfies all the checks in the verifier. And so the first set of hash checks is that, is this x0 hash equal to the hash of the other elements? And then this input checks if the hash is corresponding to whatever this input accumulator is and whatever this preimage is. And so we can just cook up this instance here by just setting it to some arbitrary instance where the x0 hash is the hash that's literally in the check, and this x1 hash is literally the hash of whatever is checked in this constraint system. And so because we cooked this up and it doesn't need to be satisfying, so let's see. So these elements get folded and one step of this, the primary function gets applied and gets put into this x1 value here. And so since we never check the x0 value in the secondary constraint system, we can just put, arbitrary trash values here. And so that's the reason why I've labeled in red instances that don't need to be satisfying. And so now, this is just the satisfaction of the normal constraint system. So since we've successfully satisfied one execution of this constraint system, we now have an instance that's satisfiable. I said at the beginning of the presentation, we're able to generate trivial pairs, which are satisfiable. And so now the accumulator for this single step will just be some trivial accumulator. We fold both these accumulators into this final accumulator. And so because both of these are satisfiable, this accumulator will also be satisfiable. And since we cooked up the malicious instance to have the original base value, the number I-1, and also the preimage we desired, this new strict instance will end up proving the successful evaluation of the sort of final IVC step. Okay, so I'll just take a moment to just leave this slide here. So in summary, we're able to run the IVC prover for a single step, but on malicious inputs, such that they don't actually have to satisfy the constraint systems. And it's because the verifier doesn't have to actually check this x0 hash here. So the key idea of the attack is just run the honest prover, but on malicious inputs. So let's see if all the checks pass. So is this a strict instance? Yes, because we actually were able to successfully run one iteration of this constraint system. Are both pairs satisfiable? So this is actually one iteration of the constraint system, so it is just satisfiable. But this accumulator here is now the folding of this strict instance, which is satisfiable, and this trivial instance, which is satisfiable. And so by completeness of the folding scheme, this must also be satisfiable. And so both of these pairs are satisfiable. And now, does this x1 hash equal to the hash of the original claim? Well, if we look at this constraint system, this hash is equal to this hash, and so we're actually good. And so we pass all of the verifier's checks for this pair. And so now the attack just symmetrically generates the pairs for the other half of the proof. And if we just put those two halves together, that'll actually just be a completely satisfying proof for I iterations of whatever function for the IVC verifier. And so we actually implement this attack generically for any choice of functions, and we generate a fake proof of 2 to the 75 iterations of the min-root VDF in only 116 milliseconds. And so, yeah, so that actually proved that the attack was a real attack. So in conclusion, the moral of the story is when you implement something, always make sure that there exists some proof of security, that someone actually went through the arguments to prove that it was actually a secure implementation. And now there's an efficient compiler from folding schemes to IVC. Cool. And that's the end of my talk.
Awesome. Thank you so much, Wilson. That was a fantastic talk. But yeah, we'll go ahead and open it up to Q&A. For the researchers inside of Spearbit DAO, Pablo has made an announcement with a link into a channel where you can ask questions. For those that aren't inside the Spearbit Discord, we have, you can go ahead and comment below on the pinned tweet on the Spearbit Twitter, and we'll go ahead and get your questions. So we'll give it a minute. If anybody has any questions, you can comment on the Spearbit pin tweet, or if you're inside of the Spearbit Discord, you can leave a question inside of the channel that Pablo made in announcements. Okay, let me take a peek. Give me 1 second, Wilson. I'll read off whatever I see. Just 1 second. So here's one question. How did you end up stumbling across the bug?
So I was actually just trying to, so there was no description of how Nova was actually implemented over a cycle of curves. And so Dan and I wanted to basically write like a summary of like, what are all these like folding schemes, what are all these IVC constructions, and how do they actually work, but in a way that's easy to read and also the proofs are provided. And so I was like trying to find a description for how this the Nova implementation actually used the cycle of curves. And so I looked at Justin Thaler's textbook, which is called Proofs, Arguments, and Zero Knowledge. And he had a little like footnote about how you actually implement Nova over a cycle of curves, but like it didn't really give a description. And so I basically reverse engineered the original Nova implementation to like see what the overall protocol actually was. And then I was like, okay, there's no way this works. And so then there's like no constraints on this X0 hash. So then I just cooked up a short little proof of concept, and the proof like accepted. And I was like, what? There's like no way this is true.
Mhm.
And so I like wrote up what I found, and I emailed the author of the Nova implementation. His name's Srinath, and he was like, "Oh yeah, this is real. Wow, I can't believe this is a bug." And so then we just wrote up. We were thinking about fixes, and so we brainstormed some fixes, and then we wrote up the paper, which basically describes the bug and also the fix.
Awesome. Next question. So, what takeaways from this finding do you think that ZK developers should use or be mindful of when they're creating their own implementations?
And so, okay, this is like a little bit tricky, I guess, in the sense that so by ZK developers, do you mean the people developing snarks or the people using the zero knowledge implementations?
The folks that are using the implementations.
So I think yeah, so one thing is if you're using an implementation that doesn't have a white paper or doesn't have any security proofs, then you should be a little bit cautious in the sense that, I mean, Nova did have a paper, but they didn't have a paper describing their actual implementation. So the protocol that's in the original Nova paper is different from what's in the actual implementation. And so these people were using the Nova implementation as a black box, but they didn't realize that it was actually broken. And so, as I was saying, you should be a little cautious when using things that don't have any proofs, especially if there's such a core primitive.
Gotcha. Awesome. Um, and then one more question. Um, let's see. Ah. As you were going through the process, or let's say before you even started, um, do you have any recommendations for folks that want to get into ZK security or zero knowledge proofs in general that are already in an adjacent, field of security? Any resources or recommendations on diving in?
So I guess it depends on what level of introduction people are looking for. Um, if you're looking for a more formal introduction to zero knowledge, I think Justin Thaler's textbook Proofs, Arguments, and Zero Knowledge is a great introduction. Um, but if you're looking into more of like a, let me think, like what snarks are or what zero knowledge is, I believe he also has like an informal set of blog posts that he wrote for A16Z. I think there's like a couple of blog posts, but that gives a pretty brief introduction. David Wong also has a YouTube channel where he goes over the construction of several snarks and what they intuitively do. Um, what else is there? I think there's also a textbook called Moon Math or something that's written by some zero knowledge developers. So that might be kind of interesting too. There's also some GitHub, which is like awesome ZK resources. So hopefully that has like a bunch of different things. But really, I think it's gonna just. I think the proper way to approach it is to be a little bit uncomfortable first, and maybe take a deep dive into some of these more formal textbooks.
Awesome. Yeah, thank you for that answer. And we have one more question. So, what would have been a real world consequence of this bug, especially in how it gets used in ZKVMs? And could you cook up a real world hack?
Yeah, so we just had a complete. So I implemented the attack generically for any choice of function. And so if this had been used for a ZK EVM, we would have been able to generate a false proof, just like entirely for an arbitrary set of starting values and an arbitrary ending value. So it just would have been a complete soundness issue. Um, and so uh, what was interesting is that I think the Ethereum, the privacy scaling exploration people, so the Ethereum people, were interested in using Nova. I think in the future for I guess this EVM type stuff, and so and I guess also the scroll people. So if this actually ended up being used without someone finding the bug, then it would have. I mean, it would have been a huge catastrophe. I think.